correct? Follow? So to do that, you use a good old math. You know G? You know this guy? G of j omega, monic magnitude of G of j omega. Alright? You use this to calculate by differentiating and setting to 0. You know, when you differentiate something with respect to the expression and set it to 0, you can find your maximum, correct? Okay, and that's what we will do. So it's down here. So mod G is actually given by this term where U replaces the omega over omega n. Okay, that's what U is. So now if I differentiate mod G with respect to U and set it to 0, I should be able to find my maximum. And also, what is the U value that gives you that maximum, which we call UR. So if I go through all the maths, alright, I will find that UR is given by this. Square root of 1 minus 2 zeta squared. Alright? And so the resonance frequency, in that case, is given by omega n square root of 1 minus 2 zeta squared. That's your resonance frequency. That's why I said the resonance frequency is not omega n. Now for this to be true, obviously the thing inside the square root must be positive. You cannot have an imaginary frequency. Right? So for the thing in the square root to be positive, then it means that 1 minus 2 zeta squared must be greater than 0. Right? 1 minus 2 zeta squared must be greater than 0. So 2 zeta squared must be greater than 1. No, yes. I put this over there. So zeta must be less than 1 over root 2 if the square root is to be positive. Okay, and 1 over root 2, 1 over root 2 is 0.727. If that is to be resonance. Okay? Alright. So now we found the resonance frequency. We can substitute it back inside here, and you will be able to find the maximum magnitude of the frequency response, which we call it as MR, is given by that expression 1 over 2 zeta square root of 1 minus zeta squared. Okay? Now you don't need to prove all this. It's in the formula sheet given to you. Right? Okay. In fact, over the Saturday clinic, we did a question like that. You asked me. Yeah. Right? Although I haven't taught you yet. Okay. Right. So this is a second order system. Alright? Okay. So again, the procedure is the same. We find the low frequency asymptote. We find a high frequency asymptote, but because now you have a zeta term, zeta determines whether you got resonance or no resonance. If zeta is less than 0.7, you got resonance. That means you got a peak there. If zeta is greater than 0.7, no resonance. That's all. Okay. What about the phase? So far, we only concentrated on the magnitude. The phase is the same thing. So if you look at the expression, which is over here, this guy here. Alright? We clean it up. Alright? And so now you see that this is the real term and this is the imaginary term. So the phase is arctangent minus arctangent of B over A, which is this guy here. Okay? Arctangent B over A. So minus arctangent of B over A. Okay, so I will erase this part. Here. Okay? So this is real, this is imaginary. So angle of G of J omega will be minus arctangent of E over A. This is what you have over there. So again, let's look at the asymptotic behavior of phase. What happens when omega is 0? This is 0 over 1. Right? 0 when omega is 0. You got 0 over 1 because it's also 0. So arctangent of 0 obviously is also 0. Okay, so that's the first condition we should mention here. What happens when omega equals omega n? When omega equals omega n, this is 1, this is 1. So 1 minus 1 is 0. Anything over 0 is infinity. Arctangent of infinity is 90 degrees. Okay? So that's the second one here. What happens when omega is very large? When omega is very large, this term is bigger than 1. Correct? So I can ignore this, ignore the 1. And then one of the brackets will cancel because it's a square at the bottom, this is not a square. Correct? Okay? And again, if you go through all the maths, you get minus arctangent of something over infinity, which is 880 degrees. Alright? So with that, you can now plot the behavior of this second order system. We know that at 0 degrees, or close to, at low frequency, it will be at 0 degrees. So that's the horizontal line here, that's your low frequency asymptote. At high frequency, it's at minus 180 degrees, so there's another horizontal line here. And at omega n got minus 90 degrees. Omega equals omega n is here, minus 90 degrees. Okay? Alright? So that's how. And how fast it changes will depend on zeta. As you can see that. Right? If zeta is 0.1, it changes over a very narrow range. If zeta is 1, you see, it changes over a much wider range. So this is zeta 0.1, zeta 1. Okay, how fast it changes will depend on zeta. Okay? So that is the phase mode plot. Any question? Phase mode plot. Okay. Now we go back to lag. Talk about lag. In many systems, you normally things don't happen instantaneously. There is usually a delay. Okay? So when you have a delay, you have this term there. E to the j omega td, where td is the delay. Alright? So when that happens, your response will have this e to the minus j omega td term. Alright? So that means if that was your gs, your response will become something that looks like this instead of this. Okay? Actually, not that it doesn't matter. Right? So originally you have this g of j omega. Now when you have delay, you will have this. This one. This is no delay, this delay. Okay? No delay, delay. So if I do magnitude, This is no delay. If I have magnitude then right? Because magnitude is 1. Correct? This is the same as this. So, when you have a delay, the magnitude both plot don't change. It's the same. It's not affected. Alright? What about phase? Alright? This is the phase. Whatever J or G is doesn't matter. Right? Similarly, what is this? That is the phase. That's the phase. That's the change in the phase. Alright? Whatever was the original phase, you have this extra term. That's the phase. Which is the function of omega. Now what happens when omega is infinity? Very large, very high. The phase also be minus infinity, right? It is very large. This will be minus a very large value also. Okay? So what that means is that when you have a phase delay, because I changed it to degree, this is in radians. Okay? When you have a delay, so far you notice for the first order and second order, the first order high frequency asymptote was at minus 90 last week's class. This evening, first thing I teach you, high frequency asymptote of second order was minus 180. It flattens out. You notice here? See? It flattens out. When you have a delay, it doesn't flatten out. It will keep going down, 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 down because of this guy. The second term. To minus infinity. So if you see a phase both plot and it doesn't flatten out, okay? That means you know you got a delay in the system. That is the telltale sign that there is delay in the system. When the phase start both plot, okay, and the phase both plot doesn't flatten out. This guy will go. Alright? Why? Because of this guy. Okay? So these are all the little rules that you need to know. Maybe that's easier because I will be dropping this. Okay. So here's an example. Okay, we have a first order system, very simple, 1 over 1 plus j omega, but it has this e term and this is delay. Alright, so what I'm plotting here are the two parts. So we have E plus okay, so we basically bring it to the part. This is the original. This is the original GJ omega. And this is the elator. Okay, so the phase of this guy which we can plot using those asymptotes. Okay. So this is the first order system. That means the phase. The phase of this guy will range from 0 degrees to minus 90 degrees. Which we did last week. First order system. It range from 0 to minus 90 degrees. Okay, at omega equals to omega 1, it will be minus 45 degrees. Because tau is 1 here. So corner frequency is 1 over tau, which is also 1. Okay? So if you plot this guy, that's the blue curve there. You see, you go from 0 to minus 90 degrees over 2 decades. Yeah, we did that last week. Now this guy here, the phase of E minus 0.5 j omega So when you combine the two of them together, it will be this guy. Combine these two together. This is the green curve. The blue and the red gives you the green. So now you look at the green curve. It does not flatten. It will keep going down. Okay? Huh? It doesn't flatten. So you can see that. So that is the characteristic of a system that has delay, which is seen in the phase mode problem, not the magnitude mode. Magnitude proper is still the same. Okay, so far we've talked about first order, second order, we talked about resonance, we talked about delay. Now we look at a more general case. And once we finish the general case, you will know how to do everything already. That's it.
Here we are the blue line, right?
Huh?
The blue line.
The blue line is this guy.
0 to 90.
Yeah, we did it last week. First order system. No, it's not. Your eyes is fooling you. It is a curve. It is an S curve. But the scale is so wide, you can't see it. Alright? It is not a straight line. Huh? It's a very gentle. Okay, so now we know what to find out about a general system. Okay? Okay, so now let's suppose we have a general expression here. Okay, in this general expression, the transfer function, as you can see, has a gain, steady state gain of k. It has m zeros here. Alright, m zeros here. Okay. Then there is a repeated pole here. Repeated how many times? Capital N times. And you have little n number of poles here. Okay, so the total number of poles is n plus n, right? The denominator. Total number of zeros is m. Correct? is n plus n minus m, that's what we call it. Pole zero excess. That means the extra number of poles compared to the zeros is n, capital N plus little n minus n. Okay? So, again, let's start looking at asymptotes. Suppose very small omega. Omega tends towards 0. If omega tends towards 0, this is very small compared to 1, so it's approximately 1. This is very small compared to 1, approximately 1. So all the brackets become 1, right? Similarly, at the denominator, this will become 1, 1, etc. So all you're left with is this guy over here. Okay, it's this guy. So if omega is very small, okay, so it reduces to k over bracket j omega to the power of n. Okay, so again you can plot the magnitude and the phase. If you do that, alright, you have that. Right, this expression. So g of j omega, when omega tends towards 0, is approximately k over j omega to the n. Alright? So g of j omega, given omega very small, and you want to find the dB value, it will be approximately 20 log k minus 20 n log omega. Alright? Not minus last one, because everything is negative. Because it's denominator, that's why it's not. Okay? Alright? This, of course, is a constant. This is a linear function of omega. So it starts at this value and it goes down at minus 20. Sorry, I forgot an n. There was an n here. 20 n. Alright? So if I was to draw it, it will go down like that. So this is 20 log k, and this slope alright? So if capital N is 1, it will go down at minus 20 dB per decade. If capital N is 2, it will go down at minus 40 dB per decade. If capital N is 3, it will go down at minus 60 dB per decade. Okay. Also notice, when omega equals to 1, okay, you have 20 log k. That means it's at omega okay, because it's 0. 20 n log 1 is 0. You're only left with this. Okay, we will use all this afterwards because we have an example later. Alright, then it will make sense. I know there are a lot of rules to remember. Okay, so one of the things you should do is when you do your revision, you should write down what are all these rules. That's your A4 sheet form. Because this is being described in about 7 or 8 slides. You can write down the rules in one tiny little corner of your A4 sheet. Okay? Any questions so far? So you can see that the phase plot also can be seen, because if this is the guy, then the phase is here, right? Right? J1 K over this. Alright, so that is at minus 90, right? So let them see. because it's n times. Alright? And what is this guy? Minus j is pointing downstairs, right? Okay. This is the constant, so this is 0. Okay, real number, constant. Minus j omega. Complex numbers. Yeah? Minus 90 degrees, right? Okay? Alright, so that's what this is telling. N times minus 90 degrees. So again, if n is 1, capital N is 1, then it will be at minus 90, flat, independent of frequency. If capital N is 2, it will be minus 180 degrees. We saw that before. That was your integrator when capital N is 1. We did it last week. The integrator, the phase, is independent of frequency at minus 90 degrees. Differentiator was at plus 90 degrees. It's in your notes. Last week we did that. Okay? So that's the first guy. Huh? Which is this here. What about the other poles and zeros? That's what we're going to do now. Okay, the other poles and zeros. Alright, now let's look at the high frequency response. When you look at the high frequency response, all the terms here, the j omega t term is greater than 1. Alright? J omega t terms is greater than 1. And then all the omegas will start cancelling as a result of that. The top and the bottom. Okay? Because you got, on the top, the numerator, you have a total of m omega terms. Correct? In the denominator, you have a total of capital N plus n omega terms. This guy that belongs to n will still stay there. So what you're left with is this minus this at the bottom. Alright? And so, what you have is this guy now. So, you have k times Ta, Tb, Tc up to Tm in the numerator. And then the denominator, you have T1 up to Tn, and then the remaining j omega terms, which is based on the difference of these two. The denominator terms minus the numerator terms. So you get this expression. Alright, again, if you change to dBs, it will look like this. So all the constants you bring out here, the term that has omega is down here. And what do we see? We see that it is a linear function of log omega, and the slope is 20 times minus 20 dB times the pole axis. Minus 20 times the pole axis. That means when omega is very large, the asymptote will be a line that has a slope of minus 20 times the pole axis. Minus 20 times the pole axis. Now you can also show that for the phase up, but we're not going to go through the whole thing. We're not sure. Okay? Now this is the theory behind it. And we're going to use this theory now to reverse engineer the both magnitude and phase plot to get back our transfer function g. That's what we want to do. Okay? Alright. Any questions? Alright, so these are all summarized. I won't go through it again. Okay? Alright? Here. Okay, so this is another summary. Can see here. So in the first one on the left, you have a flat transfer function, okay? So the both magnitude plot will be just flat at 20 log k, whatever the value, okay? And a phase of 0 degrees. Okay? Phase of 0 degrees. You know why it's 0, right? Do you know why it's 0? Anyone want me to explain why it's 0? Put up your hand. Or no? Okay, good. Okay, the next one is an integrator. So we did this last week. So the integrator has a slope of minus 20 dB per decade and a phase of minus 90 degrees. Okay? We did it last week. Now we look at poles at zeros. We did this first order system, which was a pole. Alright, I started this lesson today by revising this just now. Okay? So the low frequency asymptote is at 0. The high frequency asymptote has a slope of 20 dB per decade, and the intersect at the corner frequency here. Okay? And that corner frequency omega c is 1 over tau. There you go. It's 1 over tau. That's the corner frequency. Alright? At the same time, the low frequency phase asymptote is at 0 degrees. At the corner frequency is minus 45 degrees. At the high frequency asymptote, it is at minus 90 degrees. Okay, we did this last week. Now what we did not show you was that for a 0. 0 is the opposite. Instead of going down, it goes up. The high frequency asymptote goes up at 20 dB per decade. For a 0. For a pole, it go down. For a 0, it go up. And for the phase, instead of 0 going to minus 90, it will be 0 going to plus 90. So low frequency asymptote is at 0 degrees. At the corner frequency is at 45 degrees. At high frequency asymptote is 90 degrees. With this information, you are able to decipher and reverse engineer any board plot that we give to you. That's all you need to know. And seriously, that is all you need to know. Okay? Right. So we will look at a couple of examples.
他刚刚讲的，这个是勾当，这个是勾 up， 这个 cos 勾成 f 等于，这个 zero 是哪个 zero？ 是 frequency 还是那个什么？
Okay.
好像是
Let's suppose we have this transfer function.
cos 勾当
1 over
勾当的
alpha s 1 plus
这个
beta
是
s,
cos，
where alpha is greater than beta. Okay? So if I change this to j omega, you will have this term here. And then if I change it to dB, I have this term here. And then if I change it to this, break it up, I have these two terms to add. Now what does that mean? What it means is that in the both plot, you are superimposing one on top of the other. Alright? Such that the both plot for this first order system has a corner frequency at 1 over alpha. The both plot for this guy is also like that, but the corner frequency is at 1 over beta. Okay? So when you combine the two of them together, you just add it up. So for example,
口应该怎么写？口应该
we know this is true, right? So 1 over alpha is smaller than 1 over beta.
口应
It means this one is high frequency, this is low frequency. It means this
该
one,
是转角
if I was to draw it,
角度。
okay? So for the first guy, it will look something like that. And then, this is the first guy. Right? For the second guy, if I combine the blue and the green, you will go like that, you will go like that, and then when at this point here, you will go steeper. So this is at minus 20 dB per decade, and this is at minus 40 dB per decade. The red one is the composite response. That's it. For a very simple system with two poles. Two first order system. Alright? And you notice this is a high frequency asymptote of minus 40. If you look at the general expression that we had earlier, here, right? We say the high frequency asymptote is minus 20, capital N plus N minus M. So it's minus 20, capital N plus N minus M. So in this case, we have capital N is 0, N is 2, M is 0. So therefore, minus 40 dB per decade. There's no little n because there's no 0. Yeah? So that is explaining the high frequency asymptote. Now you get the same thing for phase as well. Alright? So for phase, what will happen is, so let's see that picture. So it's on here. Yeah. I don't have the a pole at 0, s equals 0. Do I have this term inside here? I don't have that term. I got 1 over 1 plus alpha s, 1 plus alpha b, beta, 1 over 1 plus alpha s, 1 plus beta s. I only got 2 poles. So J n bracket capital N. Capital N must be 0. There's no such term one. This is a general expression. Similarly, I don't have any zeros on the top. Correct? So my little n is 0. I only have 2 poles at the bottom. That's it. Okay. Alright, this is just to show you all the proofs. So as you can see here, originally it's flat, then minus 20, then minus 40. Okay? Yes. Now you can do the same thing for the phase, alright, and this is what you get. So I think I do the same notation, blue, red, and green. Alright? The same thing for the phase. Alright? I'm not draw, I think it's a clear diagram. So again, for the blue, the minus 45 degrees is at 1 over beta in the column. The minus 45 degrees for the first pole is at 1 over alpha. Alright? So the blue one, the asymptotes are shown here. The red one, the asymptotes are shown here. So when you combine the blue and the red, you get green. And now, you find that the green high frequency asymptote is at minus 180. Because minus 90 plus minus 90 is minus 180. Yeah? Okay? Okay. Any questions? Alright, now with this simple principle, now if you are given any expression, you can always draw it. Similarly, if I gave you the plots, you can also determine what are all the TAs and the T1s, T2s, T3s, whether there is a capital N, and also the value of K. can determine that now.
他刚我就听他说一个 high
Alright.
frequency，然
And
后
again,
慢慢
this is a
慢
summary
慢
of
讲
all
太快
that stuff. Alright, so these two slides summarizes all the essential rules. Okay? But it's hard to remember the rules without putting that into practice. Right? So to do that, we will then do an example. Suppose I gave you this. This on the left is the magnitude Bode clock. On the right is the phase Bode clock. Now, what can you tell about the phase? Does it flatten at high frequency? That means it got delay. This guy has a delay inside there. Right? Okay, if you look carefully, I can't really draw on this. So I think what I did was